Hello, my name is Dr Jonathan McKendry. I'm from the Institute of Photonics at the University of Strathclyde in Glasgow, and today I will be presenting some of our recent work using ultraviolet LEDs for high-speed optical wireless communications. And this is work that's been done in collaboration with our colleagues at the Ferdinand Braun Institute in Berlin, Germany. Here's an overview of my presentation. First of all, I'll discuss ultraviolet optical wireless communications and why we are interested and motivated to use ultraviolet light to transmit wireless optical data. Then I'll introduce the particular LEDs that were used for this study and their behavior and characteristics. Then I'll introduce some of the optical wireless communications terminology that will be used in the subsequent line of sight optical wireless communications data transfer results. And then I'll finalize with a short summary and a future outlook of where this work will go in the future. Now I'll introduce why we are interested in using ultraviolet light for optical wireless communication. So first of all, if we can operate the link in the UVC part of the spectrum between 200 and 280 nanometers, we can essentially operate in a noise-free environment where there's little to no ambient background to compete against, either from artificial or natural sources, unlike in the visible and the infrared. Furthermore, if we look at the concept of non-line of sight optical communications, which is illustrated in the figure on the left, this would be where you don't have a line of sight path between your transmitter and receiver, but instead aim to use scattering from the atmosphere in order to scatter your signal to towards the receiver and to create a non-line of sight link. Now, really, scattering is inversely proportional to the fourth power of the wavelength. So if we can use short wavelength UVC light, we will have stronger scattering compared to visible and infrared, and potentially a more robust non-line of sight link. And then if we look at the general trend in the development over the last 10 years or so of UV LEDs, on the figure on the right you can see the external quantum efficiency versus wavelength, and now you can get UVC LEDs with wavelengths ranging from around 220 nanometers and longer, with reasonable efficiencies and output powers. And LEDs are particularly interesting candidates as optical transmitters due to their high efficiency, high power, high modulation bandwidth, and low size and weight power requirements compared to conventional UV sources such as mercury flash lamps. Now, most prior work in using ultraviolet LEDs for optical wireless communication has been with LEDs with wavelengths of 270 nanometers or longer. Here we want to explore the use of shorter wavelength UVC LEDs for several reasons. First of all, for future non-line of sight communications demonstrations, there's the further enhancement to scattering, as I previously mentioned. There's a better match with the solar blind UVC region, so if your LED's peak wavelength is around 270 to 280 nanometers, then much of the LED's emission is not actually within the solar blind region of the spectrum. And then finally, there's somewhat more relaxed safety considerations. So UVC light can be harmful to the skin and to the eyes, but if you look at the diagram on the bottom right, you can see that the lowest exposure limit is around 270 to 280 nanometers, and by moving to shorter wavelengths, the exposure limit considerations become somewhat more relaxed. So in this work, we'll characterize the use of LEDs with peak wavelengths around 235 nanometers, and these devices were originally designed for sterilization applications, but here we'll show them in their application to high-speed optical wireless communications. We'll also explore the effect of micro-pixelating the LED emission area. Here we show the design of the 3 different LED samples that were used in this study. So these LEDs were designed and fabricated by our collaborators at the FBH in Berlin. The diagrams here show the designs which we will call standard S2 and S3. The red areas highlighted in the illustrations are the areas that emit light, and these are all interconnected in parallel, so the LED functions as a single emitter. The nominal peak wavelength is 235 nanometers, And one of the key things for the three different samples is the different emitting area. So as you go from the standard sample, the total emitting area on the device reduces from about 0.4 millimeter squared to 0.05 millimeter squared on sample S3. Here we show the light output power versus current characteristics for the three different samples. As you may naively expect, the largest area device gives the largest output power, so up to 1.8 milliwatts for the standard sample, as shown by the blue curve, and this is reduced to about 0.6 milliwatts for the smallest sample, S3. You can see that the blue curve in particular, how the output power plateaus, we believe that's an indication that the device is suffering from self-heating, so in future we look to improve the light output power characteristics from each sample by improving the thermal management. The next thing we characterised was the LED's frequency responses and bandwidths. So the frequency response is a measure of the LED's output signal as a function of frequency, and we measure that using the setup on the left, where we have a small signal chirped sine wave applied to electrically to the LED, and we measure the corresponding optical output with a fast photodetector. And then the frequency at which the LED's optical response reduces by 3 dB, or by half, of the low frequency value is defined as the minus 3 dB bandwidth. So the bandwidth here is essentially a measure or an indication of how rapidly or how quickly the LED can respond to high frequency signals. So the higher the bandwidth, the better it is for optical communications. And if we look at the results on the plot on the right, you can see that you can see several things. So first of all, the smallest sample, the S3 sample, reaches the highest modulation bandwidth, up to about 140 megahertz compared to about 64 megahertz for the large standard sample. And you can also see that the bandwidth increases with current density. So we believe that is because as the current increases, the carrier recombination rate in the active region inside the device shortens and the LEDs become faster. Before I move on to showing you the optical wireless communications results, I'll first of all just introduce some of the technical terms I'll use in the subsequent slides. So first of all is the bit error ratio, or the BER, which is simply the ratio of incorrectly decoded bits to the total number of transmitted bits. And as you might expect, we want the BER ideally to be as low as possible. If there are errors present in our signal, we can use something called forward error correction, or FEC. This is a method for automatically detecting and correcting errors that are present in our received signal at the expense of a small overhead. The main thing to take away here is as long as the BER is not greater than this threshold of 3.8 times 10 to the minus 3, then effectively FEC will take care of any errors we do have, and the received data can be considered to be error-free. Then there's on-off keying, which is a method of encoding the information in one of two transmitted discrete output states from the LED. So essentially, if the LED's output is brighter, then it's a logic 1. If it's dimmer, then it's a logic 0. And then finally, we also used something called decision feedback equalization. I won't have time to go into detail in this presentation, but essentially this is a technique for reducing signal distortion that occurs at higher frequencies. Here we show the results of optical wireless communication using the three different LED samples and on-off keying. So this was a line-of-sight link done over a transmission distance of about 1 meter. If we look at the plot on the left, the results without equalization are shown in solid curves, and the dashed curves represent the equalized data. So a couple of things to take away. We can see that the equalization always improves the results for a given LED, and that the highest data rates were achieved from using the small S3 sample. So from that, for the on-off keying results, we can conclude that the high bandwidth, low output power S3 sample performs better than the high power, low bandwidth standard sample and the S2 sample. And the highest data rate that we achieved using on-off keying was 650 megabits per second. Here we show a slide summarising recent results obtained through collaboration with Professor Harold Hass's team at the University of Cambridge. For this work, we applied orthogonal frequency division multiplexing, or OFDM, to the LEDs. And OFDM is an approach that is more spectrally efficient than on-off keying. So in other words, it generally allows higher data rates to be obtained using the available optical power and bandwidth compared to on-off keying. And you can see that on the table on the right. So the achieved data rates increased from around 650 megabits per second up to about 1.5 gigabits per second when using OFDM. So this figure shows how the results shown in this work compare to what has been previously reported elsewhere in the literature. So the figure shows the maximum data rate versus the peak wavelength for various publications. Publications from our group have been highlighted in red. So as I said earlier in the presentation, most of the work reported previously has been for LEDs with peak wavelengths of around 270 nanometers or longer. And as you can see from this figure, this work is some of the only work with LEDs with the peak wavelength as short as 235 nanometers. Furthermore, the data rates that have been achieved are broadly compatible to what has been reported already elsewhere using LEDs of longer wavelengths. So just to summarise, here we've reported the use of short wavelength ultraviolet-C LEDs with peak wavelengths of around 235 nanometers for high-speed optical wireless line-of-sight data communication at data rates up to 1.5 gigabits per second. This is some of the only work that's been reported so far using LEDs with such short wavelengths, and operating at these short wavelengths brings several advantages, such as stronger scattering for non-line of sight communications in future, a better match to the solar blind region of the spectrum, and possibly mitigating some of the eye and skin safety concerns. Furthermore, we've shown that micro-pixelation of the emitting area offers improved bandwidths at the expense of optical output power, and can potentially lead to improved data rates. And in future, we aim to look at some performance improvements, so things like the better thermal management that I mentioned, and then also looking at further studying the effects of micropixelation. So for example, looking at changing the pixel size, the pixel density, or potentially individually addressing the pixels to do MIMO rather than using all of the pixels together in parallel. Finally, I would just like to acknowledge the EPSRC Future Telecoms Research Hub Titan for our funding, and I'd like to thank our colleagues at Professor Harold Hass's group at the University of Cambridge for their collaboration with the OFDM, and I'd like to thank you for your attention. Thank you.